things. So let's have V and V vector spaces over some field F, and V is finitely generated. Then if we have a linear map from V to W, we have the three are equivalent statements, all right? So this is the theorem. These three statements are under these circumstances equivalent. So firstly, F is onto W, all right? So this is an epimorphism. Second of all, for any generating set of generators that consists of V1 till Vk, in the vector space V, f of V1 until f of Vk is generating set of W. All right, so what is the proof for all this? And actually, there's another third statement, so we didn't cover that one. It's equivalent also to there exists a basis that consists of V1 till Vn of V such that this set f of V1 till f of Vn generates W. All right, so these three statements are equivalent. So how would we prove it? Well, we can first do the implication of statement 1 to the statement 2, then 2 to 3, and then 3 to 1. So we do 1 implies 2, then 2 implies 3, and then 3 implies 1 as well. All right, so for 1 implying 2, what would that be? Well, for any vector in W, there exists some vector in V such that f of x is W. F is epimorphism. All right, so surjective homomorphism. And because V1 till Vk generates V, then implies that we can write x as T1, x1 as a linear combination of V1 till Vk using Tk different constants, T1 till Tk, and then W equaling f of x actually equals f of this whole x, which will, if we just rewrite it 2 more steps forward to say space here, is going to end up as this: f of V1 plus all these terms until Tk f of Vk. And we found out hereby that every vector W can be expressed, and so every vector W can be expressed as a linear combination of well, I can just verbalize it, that every vector W can be expressed as a linear combination of f of V1 till f of Vn of Vk. That means that this set f of V1 till f of Vk generates W. All right, so that's for part 1 implies 2. What about 2 implies 3? Well, this part is far shorter. It directly stems from the fact that every basis of V generates V. All right, so if you look back at it, one can imply that and see why that works out. So that's 2 to 3. So every basis of V generates V. So that was very straightforward. And let's take another page for the last of these three implications for this proof. So 3 implies 1. Well, we need to show that for every vector inside W, V has a source, and the image under F of it has an element that there's an output under F. All right, so that means that every W in lowercase w has a V in V such that F of V is W, basically. And so, because the set F of V1 till F of Vn generates W, we can write that Vw is equal to T1 F of V1, so very similar like before, plus, and a linear combination until nth constant, and F of Vn. And so for vector x, we have x equals T1 V1 until T and Vn. For which we have f of x equaling, and we basically just put it there, so we get a very similar case like we had before, where this time is until nth element, so f of Vn. And that is equal directly to W. And so f is onto W, the capital case vector space.